Okay, fine.
So it is happy to know that. So good morning, everyone. So shall we start the program? Sir.
Yes.
Vengadeshan sir, please start.
Thank you, sir. I would like to welcome you one and all who are gathered here for today's International Faculty Development Program on Advanced Functional Materials, Energy, Environmental and Sustainable Development. And day 5, session 1, who is presenting the work, Dr. P. Sathiyanathan, postdoctoral researcher, Soft Robotics and Intelligent Materials Lab, Department of Mechanical Engineering, Korea, Advanced Institute of Science and Technology, Republic of Korea. He has completed his PhD degree in Vellore Institute of Technology, and he has received so many awards like Junior Research Fellowship, International Travel Grant, and as well as a Research Associate Award. And he has published 25 research journals in international and national level peer-reviewed journals. Now he is working with Korea and several countries. He has worked as a postdoctoral as well as a faculty member as a Mahatma Gandhi University, Kerala, and Adi College of Engineering Technology, Agni College of Engineering Technology, and Karpagam College of Engineering and Technology. And he has received 25 number of publications, and also, 2 more papers have commented in the reputed journals, and 1 patent has done in the research work in the field of biopolymer composites for high performance triboelectric energy harvesting applications. Now I would like to hand over the session to the chief guest for addressing the sir, please.
Yeah. Good morning, everyone. Thank you, sir, for the nice introduction. So today I'm going to deliver my talk on biopolymer composites for triboelectric energy harvesting applications. So shall I start? Hello. Hello, sir.
You can start, sir.
Yeah. So good morning, everyone. Thanks for the nice introduction. So I'm going to deliver my talk on biopolymer composites for triboelectric energy harvesting devices. So I'm working as a postdoctoral researcher in KAIST, Korea. So this is the introduction about KAIST. KAIST is the first public research-oriented institute in Korea, and it is one of the most prestigious universities in the nation. So it holds Asian University ranking 10 and QS World ranking around 56. So I shared some of the pictures of the university. So it is a very big campus. So I have showed the arrow mark here, the entrance, and I'm working in this building, which is N27. It's about 1.5 kilometers from the entrance. And the Korea Institute located in the center of the Korea, which is about 150 kilometers from the airport, international airport. So the contents of my introduction. So I'm going to contents of my talk. I'm going to give the introduction about triborate nanogenerators, and then the chitosan cough based TNG, which I have fabricated and published work, and the application which I demonstrated using this chitosan cough TNG system, and then the summary. So moving to the introduction. So I would like to start with this slide. So since I'm going to talk about the triborotic energy harvesting systems, which is an energy generator, so I would like to talk about the global energy consumption from 2000 to 2022. So if you look at this chart, the most of the energy for our needs rely on these three major resources, natural resources. One is coal, oil, and natural gases. And also we rely on nuclear energy, hydrothermal energy, and other renewable systems. So most of these systems are non-renewable, which similarly, I mean, like the meantime, it also causes global warming and climate changes, which is a major issue. So we cannot rely on these sources for the future. So we need to find alternatives to 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 make to protect the earth and also make the things sustainable. So what are the energy sources available for the future? So if you look at the technological revolution in the human history, it is very closely related to the energy, because based on the energy development and the technology, the industrial revolution takes place. If you look at this chart, in 1780, industrial revolution 1.0, so the machineries comes into action. So there were many industries which working on machineries and automations. So in those period, the most of the energy production relies on the coal and oil. And similarly, industrial revolution 2.0 for the mass production and the and like at that time, during that time, the 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 assembly line, electricity assembly line takes place. So and after that, industrial revolution 3.0, computer development, computer and automation industry development. So in all these industrial revolutions, we only rely on coal and oil sources for the energy. But now living in the era of Internet of Things. So we are mostly connected the cloud system and some internet systems. So in this era, most of the devices are Internet of Things, very small devices used for communication and sensing and other purposes. So these devices generally require very less amount of energy. It does not require a high amount of energy like 200 volt or 250 volt, something like that, which is just need a 2 volt, 3 volt, or less than 1 volt. It is enough to power up the system or to function these systems. So if you look at this chart, the source says at 2030, more than 50 billion devices, Internet of Things, like the telecommunication devices will be connected to the internet. So actually, do we really need a coal or oil or other gas based energy sources for these devices? The answer is no. We need some other devices. We don't need this kind of energy sources for powering up these devices, because these devices are very tiny and require very small amount of energy. So what is the feature, what is the next energy source to power up these small devices in this industrial revolution 5.0? So the question remains still remained, so and now, so to understand that, what is required, what kind of energy sources are required for powering up these small Internet of Things devices, we should understand the energy utilizations. So we observed entropy in the energy utilization. So what is that entropy? Because see here, whatever the power source like a coal plant or oil based power plant and nuclear based power plant. So these are like very order energy. It produces order energy. This order energy is used for order applications like industries, machineries, and some household things. So these are like order energy used for order applications. But we observed, since we are using Internet of Things, all these devices are telecommunication devices which are not connected with the power source, which is like it's a movable devices. So we observed some disorder applications. For this disorder applications, you cannot use order energy, because for example, if you have a smartwatch, you can only charge smartwatch wherever you go. That is not possible. So that is a kind of a disorder applications. So similarly, mobile phones, your headphones and everything, only you can use batteries to power up these devices. So we observe this disorder, like this entropy in the energy utilization system. So for this disorder applications, we need actually a disorder energy. You cannot produce a disorder energy using a coal power plant or nuclear power plant. We need some other energy sources which is dissipated in the environment. It's a waste energy. So what are those waste energy? For example, our body motion. Every humans are walking, every humans are running, every humans are speaking, doing some motions every day, doing some work. So these body motions actually you can convert into electricity, because it is this mechanical energy you can convert into electricity. So this is a pure disorder energy. So this disorder energy you can use it for these disorder applications. So how can we harvest energy from body motion, mechanical vibrations? So for that purpose, people invented these triboelectric nano generators. So this is a new era of energy harvesting device. So what is triboelectric? It's not a new thing. It is already existed in the nature over 2,600 years ago. So how it is happening? So for example, I showed a figure here. In this picture, you can see a cat. The polystyrene blocks are attracted on the cat fur. So what is happening here? How this happened? So this is called a static charge or triboelectrification. The physics people know very well about this concept, the static charge. When there are two different materials which is having two different electron affinity, they will get attracted or they will repel each other. So that is a static charge. So in this case, the polystyrene or a negative material which are attracted on the cat's fur surface. The cat fur acting as a positive material and the polystyrene blocks acting as a negative material. Hello? Shall I continue?
Please.
Yeah. So this static charge actually it's a known phenomena, but nobody knows what is happening, why this attraction takes place due to electron transfer, ion transfer, or species transfer. Nobody knows. So this concept is not fully understood, but we just observed in the environment, in the nature. So in 2012, this guy, Professor Zhongling Wang from Georgia Tech, USA, so he accidentally invented these TNG systems. He accidentally invented. He did not plan to, produce or fabricate any. He got some data, and he was very curious about why we got this data, and then he kept on working, and then he published a paper in 2012 in Nano Energy. He is also a chief editor of Nano Energy Journal. So this is the first work in 2012. So what is triboelectric nano generators? So the triboelectric nano generator basically converting a mechanical energy into electricity. This is exactly similar to piezoelectric nano generators. Piezoelectric nano generators are also invented by this fellow. So in 2006. So basically, it can harvest energy from mechanical force. That mechanical force from your body motion, your speaking or heartbeat monitor. Heartbeat signals or pulse signals. So all these produce a small amount of mechanical energy. It produces some vibration. So those mechanical energy you can convert into electricity through this triboelectrification effect. So we know that it is attracted. When it is attracted, there may be a transfer of electrons. But how can you produce sine wave signals? How can you produce AC signals? In that case, the polystyrene blocks should have to remove from the fur and then reattached. So there should be some contact and separation. Without contact separation, you cannot produce a continuous energy. You cannot produce a AC signal, AC current. So in that case, he fabricated this device and he proved that it is possible. And so what is the mechanism? What is the working principle of the TNG systems? Actually, it is based on a coupling effect, based on two effects which are coupled each other. And I will play the video. You can see the first one, contact. When it is contact, the materials are get electrified, and then when it is separated, the electrons are pulled from a negative material to positive material. Similarly, when again contact, due to the electrostatic induction, the electrons are pulled back from the positive electrode to the negative electrode. So this is how when it is contact and separated, the electrons are flow back and forth. So this is how it produce electricity, and you will get a current signal, AC current signal. Wait a minute. So you will get AC signals. When it is contact, you will get positive signal. When it is separated, you will get negative signal. So similarly, when you apply contact separation motion, it will produce autonomous continuous energy. So the first concept, physical concept, is contact electrification or triboelectrification, and the second concept, electrostatic induction. The triboelectric nanogenerator becomes realized. So sorry. So after the invention, in the beginning, in the beginning of 2012, they produced, because they accidentally discovered this thing, and then they tried to improve the energy harvesting performance of these triboelectric devices. So they come up with a different strategy. For example, modifying the morphology. Morphology plays a very important role, and modifying the chemical functionalization, doing functionalization on the substrate of the any positive or negative material. You can introduce many negative groups or positive groups or some ionic groups, so that you can tune the surface charge density. Similarly, you can incorporate some nanoparticles into the polymer matrix, and you can improve the dielectricity of the material, so that it will improve the performance. So similarly, charge injection process. So there are many strategies have been applied, and because of this strategy, they have achieved almost more than 500 watts per meter square. A recently published paper in ACS Nano, they reported 500 watts per meter square. So using a small device, 3 into 3 centimeter, you can actually produce this much energy, which is quite enough to power up your laptop, your mobile phones, and other small electronic devices. So actually, this TNG is very interesting work, because it is a 100% interdisciplinary research. You can see many physics people are working on this field, many chemistry people are working, many electronic engineering people are working, many telecommunication like ECE department people are working, many mechanical engineering people are working. So it becomes a complete interdisciplinary research. And you can also see the publications, now more than 1,500 articles per year published, particularly in triboelectric nanogenerators field. So what is the significance? Because we know that piezoelectric, pyroelectric nanogenerators, which is already existed. So what is the significance of TENG over these materials? The main thing is, for piezoelectric materials, the material should have piezoelectric property, intrinsic piezoelectric property. But in this case, you don't need to have any intrinsic property. If we have two different materials having different electron affinity, that is quite enough to make a TNG devices. So the abundance of material choices is the biggest significance of TNG system. So most of the state-of-the-art TNGs are constructed with synthetic polymers, because the synthetic polymers are highly stable in terms of environmental impacts. But like biomaterials are not that stable. Mostly synthetic polymers are stable. So the state of the TNGs are constructed with synthetic polymers and also some ceramic systems, biomaterials, functional materials. But I'm particularly interested in biocomposites. So the nanocomposites in TNG, if you look at the publications, they are publishing so many publications per year in like a composite-based TNG systems. So these composites are giving flexibility comparing with neat materials. The biocomposite, I mean the composites showing a good flexibility and robust structure and high performance. That's why I am interested in nanocomposites. So now I'm going to talk about my work, my research work that I have published recently. So moving to the next chapter, chitosan covalent organic frameworks composite tanks. So in this case, I chose a chitosan polymer, which is a biopolymer, and I also chose covalent organic framework filler. So why biomaterials? Because the biomaterials are naturally abundant. It is sustainable, biocompatible, biodegradable, and non-toxic. So these are the pros of these biomaterials. Comparing with synthetic materials, petroleum-based synthetic polymers, which also produce some environmental effects, some toxic to the environment, and it degrades the quality of the environment, water system, and the soil systems. So that's why I don't want to go for synthetic-based material. I want to go for biomaterials. So in this case, I chose chitosan because comparing alginate and diatoms and cellulose fibrils, chitosan shows good performance, and also the possibility. I mean, like the processability is quite easy. So I chose chitosan material in this case. So what is the disadvantage of using biomaterials? Because till now it shows a very moderate performance, and retaining the surface charges quite difficult, because since it is a biomaterials, it can easily absorb moisture in the water. I mean, like moisture in the water in the moisture. So it will easily absorb water molecules, and it will neutralize the charges. So the poor charge retention and moderate performance is the biggest issue of using biomaterials in TNG systems. So how can I solve this? So for this, I want to make a composite. In that case, I chose covalent organic framework as a filler materials, because it also a biodegradable, biocompatible material. So I designed this material as a biocompatible and biodegradable, which shows no cytotoxicity. So because of that reason, I have incorporated into a biopolymer chitosan, and I have fabricated this device. So this I just want to show the literature. So these are the publications based on chitosan composite system. So we published our work. In our work, we reported the highest power density, about 333.4 milliwatt per meter square, which is the highest one comparing so far the published work. So our strategy to enhance the performance. So we want to fabricate a biocompatible composite system. So we designed a biocompatible COF which possess electron donor, because the chitosan is electron donor. So if I use electron acceptor material, then it will neutralize the the performance. So that's why I want to add some electron donor material into the electron donor polymer matrix. And so for this electron donor nature, I intentionally introduce sulfur and nitrogen based ligands. So taking this sulfur and nitrogen, which is biocompatible, so the entire COF will act as a biocompatible material. And as you know that COF material has hierarchically porous structure. This hierarchically porous structure also helps to retain the surface charges, because it will capture the surface charge density. So this is the strategy. Because of this strategy, we achieved actually a high performance TNG system. So this is the COF. So there are many COF system available in the literature, but these COF systems, they have only directly taken this COF system, but the problem is durability. Because this powder, it is exist in a powder form, you can just attach this powder on the sticky side of any aluminum or copper electrode material, which is not stable actually. after over the period of cycle, the material are attached onto a negative electrode or opposite electrode. So it will neutralize the charges, and also slowly the powder calf materials peel off from the sticky side of the electrode. So the durability is a very big challenging of using only calf based TNG system. That is the reason I go for composite. So this is the synthesis of the NS calf. So we did some simple reaction, and the solvothermal reactions. We have achieved this NS calf, which is nitrogen sulfur rich calf systems, and this is the confirmation of nitrogen and sulfur present in the calf systems. You can observe you can see the color. So it is rich in nitrogen and sulfur compared with the other moieties. So how we fabricated the composite? So after the synthesis of calf, we just incorporated into a chitosan, different weight percentage from 1, 2, 3, 4, 5 weight percentage of a calf system into the chitosan, and we have fabricated the freestanding filling, which is flexible in nature. Actually, it is very difficult to achieve this freestanding filling using chitosan thing. So we have worked out. We have done many trials, and we finally achieved this. So this is the fabrication setup. You can see this. This is how we fabricated. So after cutting the calf film, this is a neat chitosan and this chitosan calf film, and we have attached onto acrylic disc on backside of the aluminum electrode, and then we connected the wire for the electrical contact. And similarly, we have fabricated the FEP. FEP is a synthetic polymer. It is as a negative material. So we have connected these two electrodes onto the mechanical shaker. One is attached on the lab jack, and one is attached on the shaker, so that it will give the sinusoidal motion. And then we connected with the function generator. The function generator is to produce some frequency, and similarly power amplifier is used to produce some power, so that we can manipulate the frequency and the force using these two devices. And finally we get the signals using oscilloscope we recorded. So what are the key factors for the enhancement in our TNG system? Because we reported the high performance, and our material showed better performance over other existing chitosan based TNG system. So what is the key factor for the enhancement? So we studied 3 key factors. The first one, electron donation. Because of the incorporating the calf system, because of the nitrogen sulfur, which is rich in electron donor, so it gives more electron donation to the negative material. So more electron transfer takes place. Because of that, more output we got. So that is the first reason, electron donating groups present in the composite system. And second one, surface roughness. When there is a good surface roughness, uniform surface roughness, and there will be a good contact between the two electrode material, positive and negative material, and through that contact point only the electrons will transfer. So, and the contact electrification takes place. So our material, after incorporating cuff system, because it is available in micro and nano scale, so it produces some roughness, uniform surface roughness. Because of that roughness, there is a very good contact. Because of that contact, a good electron transfer. Because of that good electron transfer, we get higher output voltage. So that is the second reason. And the third reason, a relative permittivity. So adding this CAF will have a very good interaction, hydrogen bonding interaction and other electrostatic interaction. Because of this electrostatic interaction and the polarization takes place, that polarization improves the relative permittivity of the composite system. So because of these 3 effects, it produces high energy comparing with the neat chitosan. The neat chitosan produce 65 voltage, whereas our composite system produce 129 voltage. So this is the proof for the surface roughness. You can see this is the chitosan, neat chitosan, and chitosan CAF. This is like there is no much surface roughness. The height of the roughness about 3.9 nanometer, but in this case 173 nanometer. So it has higher surface roughness. That's why it produces good performance. And the synergic effect, the first one's surface. So what is the proof for the electrostatic interaction? What is the proof for the improved relative permittivity? So we studied through FTIR and XPS, and we observed that among the six different weight percentage composite system, only in the case of 4 weight percentage, we observed good shifting. I mean, like a significant shifting in the 1558 centimeter inwards band. So this FTIR band shifting towards a higher wavelength. So this shift observed only in the 4 weight percentage. That's why the 4 weight percentage showed a better performance than other samples. So why this shifting takes place? This shifting due to electrostatic interaction or hydrogen bonding between the calf and chitosan system. So here we depicted the interaction. So there is an interaction between the amine groups exist in the chitosan and the OH groups present in the calf systems. So or vice versa, like here this nitrogen group will interact with the hydroxyl group of the amine system, I mean like hydroxyl group of the chitosan system. So similarly, NHNC, I mean like this N11C, this interaction between the calf and the chitosan systems. So these two interactions was observed, was proved in XPS spectra. You can see here. So there's a new band. This one for chitosan calf and this one for pure chitosan. In pure chitosan, only we observed the protonated NH peak in the chitosan system, but whereas here a new band observed here and here. So the blue color peak observed, a new peak observed. That is due to the interaction between the NH and CN of the calf systems. So this band and this band was observed in XPS spectra. So due to these two interactions, actually it improves the relative permittivity, and we observed chitosan shows are around 5, I mean like 4.9, whereas the calf system, I mean like the composite system shows around 20 relative permittivity value. So this is the proof for the synergic effect of the composite systems, and due to these effects, it produced a good amount of output voltage and current. So here see the triboelectric output performance. So 0 weight percentage to 6 weight percentage. Among them, the 4 weight percentage sample showed higher value, 132 voltage. So similarly, the current also it showed higher current, about 2.38 microampere. So for the further studies, actually we took only the 4 weight percentage samples, and then we carried out the force and the frequency dependency triboelectric performance. So as expected, when you increase the force, the performance will increase. That is already proven effect. So we also observed this similar thing in our system. So when we increase the force, the output will quite keep increasing. So it increased up to 156 voltage at the range of 8 Newton force. Similarly, at frequency, at 9 hertz, it shows 145 voltage. When we increase the frequency up to 14 hertz, the output voltage increase up to 212 voltage. But at the same times, you cannot keep on increase the frequency, you cannot keep on increase the force, because when you keep increasing the force at particular stage, the force is quite high and it will damage the sample, then your performance will reduce. Similarly, the frequency also, because the frequency also giving a good contact, it also damages the sample. So for the demonstration, I mean like for the paper research purpose, we don't need to show more than 8 Newton force or 14 hertz frequency. So we stop at this range. So after that, we calculate the power density. So in order to understand what is the power produced by our TNG systems, we have calculated, we have connected a series of load resistance into our system, and then we have calculated the RMS value, and then we calculated the power. So our chitosan system produced 29.47 milliwatt per meter square at 100 mega ohm, whereas our composite system produced 333.4 milliwatt. Actually, this equation, like this is the standard equation used for calculating the power, but people are also contradicting with this equation. They are claiming that this equation is only used for commercial devices, like very stable energy harvesting devices, like uh, like other kind of like solar or piezoelectric or other kind of system. It is okay because it produces stable energy. But for this, so for this TNG system, actually the output voltage is instantaneous, so we cannot apply this equation. So people are also claiming that we should not use this equation. So we followed this equation, and we have calculated the time average power density, which you can actually related to the our AC current or AC signal which we get in our house. So you can connect this power with these things. So using this equation, we observe our Kaitosan system produce 1.70 milliwatt per meter square, whereas our composite system produce 10.89 milliwatt per meter square. So this is the demonstration of powering electronic device and the stability. So our system is highly stable over 9,000 cycles. There is no fluctuation takes place in the the signals. So it is highly stable. And also like we connected with the different capacitors in the circuit, and we showed that the capacitors are charged using our devices, and similarly we showed illumination of different LED lights and electronic watch. So since our material is biocompatible, we want to show whether our CAF system also are biocompatible or not. So our CAF system shows a biocompatibility over up to 150 150 micromolar concentrations. It shows a very good cell viability. So it is highly biocompatible. There is no cytotoxicity observed in the Kaitosan system. I mean, like in the Kaitosan and COF system. But still, you can see some red spots. So that is due to the surface roughness, not due to the the viability of the material. So it is only due to the surface roughness. This is also a proven effect. So the applications. So after fabricating this device, after the demonstrations, we also want to come up with a different application. So for this, we gone for this urination evaluation tool. Like using our tank system, we make it as a disposable sensor, which is used for urination evaluation too. So this is the fabrications. There are multi layers used for the fabrication, and we optimize the dimension of the sensor, because only at particular dimension it actually produce signals. So for the TNG, like for the triboelectricity, even the 3 centimeter square is quite enough, because it has a very good contact. But in this case, we are just we are urinating. Actually, like urinating means we are simulating the urination process, so that vibrations are not quite enough. So we fabricated 6 centimeter square, and 6 centimeter square shows a good performance, good signals. So we have simulated the urination setup. Actually, we need patients with the bladder issues who has a urination problem, but we cannot collaborate with the like a medical institution, because it will take a longer time. So we just want to publish this work. So we simulated the setup in our lab using simple setup, and then we produce actually you can think that we cannot simulate the bladder, because the bladder has some physiological functions, so that we cannot simulate. But we actually follow some standard for the urination process, whatever the existing system available in the like in the medical industry, like uroflowmetry is the existing methodology for studying the urination process. So we follow the same standard in our experiment also. So we get different signals with a different urination process condition that I will show later. So first we get the signals we collected through the oscilloscope. That signals we did processing, and we are normalizing using some factors, and then we did some we did some spectrogram, and after the spectrogram we gone for deep learning process. So this one is the different conditions we followed. So there are multiple conditions, multiple intervals we used. So each data, like for each intervals, for each flow rate, we actually taken 6 times the data to show the reproducibility, and all the data are highly reproducible. So to make it, the system works effectively. So these are the conditions. So these conditions are closely related to the medical standards. The flow rate, voided volume, and the maximum voided volume, all are closely related with the medical standards. So after collecting the data, actually we train the data sets through deep learning, that is artificial intelligence. So why we develop these things? Because so now we have this data, so we got some signals, but we never know like how can we interpret the signals, and how can the doctors can interpret the signals. So we come up with this deep learning algorithm, and we produce some identification over the signals. So the yellow color shows some values, which is called as the confidence value. So this confidence value, like it can detect the system, it can detect the signals, and it will show some values. So if these values are less than 40, then you cannot use this system, or maybe the data will be a wrong data, which is not reliable. So we want to make it all the data are above 40 or 50% confidence value. So to achieve this, we actually train these data sets. We have fabricated many sensor systems, and then we produce these data sets. Now in all the samples, we achieved that confidence levels. So if we look at this, all the systems shows more than 40% like 0.40 percentage. So through this, we can detect whether the patient has normal urination or abnormal urination, or many different intervals, or slow flow rate, or higher flow rate. Those details we can study. This is a little tricky to understand. So in this case, like when you urinate, it produces some signal because of the vibration, because of the impact, it produces a signal. So if the person has a healthy urination process, only the first time the urine, when the urine impact on the sensor, it produces signals, and after that no signals. So which means his urination is very continuous, there is no gap in between. But if the person has some bladder issue, he may has some breaks during the urination process. He has to push his bladder to urinate the urine. So when he has a bladder issues, he will not go for like a normal urinations. There will be a discontinuous process flow. So that discontinuous flow you can observe, and for each discontinuity, for each break intervals, you will get some confidence value. So through this, actually doctor can easily understand whether the person has a bladder issue or not. So this is basically a early stage detections. We are not claiming that using this we can detect a bladder issue. We are just saying that through this cheap, easily fabricated sensor, you can, in your home, you can actually test your urination, and that signals you can transfer to doctors, and the doctors can give you some inputs, whether you have to go to the hospital to check whether you have a bladder issue or not. So this is like some early stage detecting systems for the urination application. So this is the hypothesis of our work. This is our published paper in advanced materials technology. So like you have a devices, like in future, if we fabricate this device, if it become commercial, you can buy this DI tank system, and you can just urinate, and you will collect the signals through wirelessly, and that we will, using some software, we will process the signals, and then we will send the signals to the mobile applications. So doctor easily can detect, oh, this guy has some problem. So this is the hypothesis of our work. But to make it to make this work, we have to collaborate with doctors, and we have to come up test with some patients to confirm this study. But that will take quite long time, so we don't want to wait. So we just provide a tool, we just provide algorithm, so that in future somebody can work on this particular application. So this application has the potential to use it for a telemedicine thing. So the conclusion of my work, So we have fabricated COF. I mean, like we have synthesis COF system that we have incorporated into chitosan, and we have fabricated a chitosan COF TNG system, which is biocompatible, biodegradable in nature, and the improvement for this thing, for this enhancement of the TNG system is surface roughness, relative permittivity, and electron donation. And since we synthesized biomaterial, biocompatible COF material, we wanted to examine the cytotoxicity, and the cytotoxicity affirming that our material has good biocompatibility. So the potential application in telemedicine applications. So I would like to acknowledge and I would like to thank my group members, my professor is there, and all my stream members, KAIST. So I would like to mention two people. So this guy, so actually he did the simulation part. He did the deep learning process because he's good in the. I'm like he's a good engineer, so he did the process, and he's the second author of my work. And this guy, so he was collaborating with me, and he actually helped me a lot for the TNG thing. So I would like to thank all of them. So thank you for your attention, and if you have any questions, please raise. Thank you.
Sir,
Yes, sir.
thank you, sir. Thanks for your enlightened talk, sir. There is a question in the chat box, sir.
Yes, sir.
Participants, they can.
Okay. Okay. So how different from a Van der Graaf's generator? Okay. Van der Graaf generator. Actually, like the Van der Graaf generator, like a commercial electromagnetic generator. So this commercial electromagnetic generator actually will work at particular frequency, and it works based on the electromagnetic induction process. So the biggest difference from this electromagnetic generator and our TNT system, the electromagnetic generator will work effectively at particular frequency. For example, like you cannot harvest good energy from electromagnetic generator at 0.1 hertz. You need some hertz. For example, like imagine our household electricity. Our AC signals are 50 hertz. Only at 50 hertz, like the signals are 50 hertz. So at that 50 hertz only, it works. It produces that much current, that much energy. But TNG systems, you don't need that much frequency, that much force. Even 0.1 hertz is enough. Even at 0.1 hertz, you can produce energy. That energy can be useful for tiny devices. But electromagnetic generator, you cannot operate at 0.1 hertz. You need some minimum frequency. Actually, I did not show that slide. I had, because of the time constraint, I removed some slides. So our TNG is linearly dependent. Frequency is linearly dependent. You can use our system at small hertz, it produces small energy. When you increase the high frequency, it produces high energy. But the electromagnetic generator will not produce energy at low frequency. Only at particular frequency it will produce energy. So that is the big difference. And the energy density measured is in a small scale. What are the challenges in producing large scale? Yes, like like for the research purpose, like nobody constructing like large scale TNG devices actually, because that is you can actually like you can actually produce, as you mentioned, there might be some challenges, because whatever we produce 3 into 3 centimeter square, but if you produce actually a 10 like a 1 meter square or more than 1 meter square, then there might be some challenges in the means. See, 3 centimeter square, we are applying some force. That force is uniformly distributed on the on the TNG system. Just imagine if you have a 1 meter square, a very big TNG device. In that case, you cannot achieve the same amount of energy, because, for example, people are walking on the TNG mat, okay, at only particular place they are touching, which means the whole 1 meter square area is not activated. Only at that foot point only it is activated. So you cannot compare the same energy, amount of energy. But in the 3 centimeter square, it is 100% it's activated. I mean, the whole area is activated. That's why we are calculating that much energy. So yes, in practical, when you make a large scale, there are some challenges. And yeah, thank you for your appreciation, new innovative ideas. Yeah, thank you, sir. And you have carried out the confidence level using AD. What is the probability of getting the false positive? No, sir. Actually, that is why we have repeated, 6 times. We have repeated the measurement 6 times for each samples, because we also thought in the beginning. So actually, I showed only very few slides. Actually, for the optimizations, we have fabricated many devices and we took many time. So the confidence level is highly reliable. Whatever we achieved is highly reliable. So, but there may be possibility like in our system, like we optimize these things. Maybe if someone in the future, if they develop if they develop TNG system using different materials, in that case maybe they may get false positive. But only if someone using our algorithm, our pattern, our algorithm to make this similar experiment, in that case we can compare. So otherwise, otherwise we don't need to worry about that thing, because whatever we develop is for our system only. Yeah.
Thanks for your enlightened talks, sir. Thank you so much, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Yes, sir.
So,
Can I sign off now?
dear participants. Yes, sir. Yes, sir. Please, sir.
Thank you, sir. Thank you, sir. Thank you, sir.
Yes, sir. Thank you, sir. And dear participant, we have another session also now. So we have one session with Dr. Abu Hafsa Alusami from Department of Physics, Institute of Natural Sciences and Mathematics, Ural Federal University, Edinburgh, Russia. He has some postdoctoral experience on the solid-state mechanism and in the same institute. His research interests are ion-based superconductor, glass composite, and polymer composite, dye-sensitive solar cells. He also interested in the phenol nanofarads. So we have the guest with us. So before his talk, we have to play one video with us, one felicitation from our guest. Yes, sir. என்னோட screen share பண்ண முடியல.
Hello, everyone.
Yes, sir. Just a minute, sir.
Yes, do you hear me? Do you hear me?
Just a minute, sir.
Okay.
Yes.
Really, I am very sorry. I have a problem
Yes, sir,
in the
please,
connection. I have
just a minute,
really,
sir.
I
1
am
minute.
very sorry. I have a problem in the connection, but I
1
will
minute,
try
sir.
to solve it.
Sir, 1 minute.
Do you hear me? Do you hear me? Good. Yes.
Development from 26th February, the March 2024 through the online mode. I understand that there's a wide range of illustrious speakers from India and also from the other countries. I hope that this conference and FTP will be able to bring a new trend in chemistry and material science research.
Okay, I am waiting you.
I'm sure that the physics faculty and the chemistry faculty from different colleges and also the research students and also PhD students and industrialists can be able to get a lot of knowledge from this FTP. I'm very much happy to know that my dear friend Saktivanti Kadrishan is the convener of the program. I wish all the best for the entire organizing team, the staff, TRP, the Vision. Thank you very much and wish you all the best.
Thank you, sir.
Dear
Thanks.
colleagues and friends.
Thank you. Thanks to Dr. Ranjit Thomas for this video. Now we'll go for a presentation. Yes, sir. Now you can start, sir.
Yes. Hello, everyone. At the first, I want to thank you for this chance. And I want to thank my colleague for the great opportunity in the first session. Thank you very much for him. At the first, I want to say sorry for everyone because I have a bad connection, and I tried a lot of time to solve it, but I have a problem. Sorry. I am Abu Khasba Ali. I am. Do you hear me? Yes. Hello. Yes. I am Abu Hasba Ali, Department of Physics, Manufaa University. I am postdoctoral researcher in an Institute of Nature Science and Mathematics, Oral Federal University, Ekaterinburg, Russia. Today I will talk about structure, dielectrical and optical properties based on spinel ferrite nanoparticle filler reinforced PVA for optical, electronic, and energy storage devices. Okay, I will talk about the importance of the PVA polymer and about the spinel ferrite technology. Uh, uh, yeah, Technology has paid a great attention to polymer material due to their important chemical and physical properties. Due to extensive use of solid polymer material in electronic devices like mobile phones, laptops, and notebooks, computer, poly PVA is very important material due to exponential film forming capacity. And spinel ferrite nanoparticles are used in technology application by controlling their microstructure, particle size, and cation distribution at octa and tetrahedra, which also aid in changing the physical properties of polymer and getting new polymer material. It is used in variety of fields, including microwave absorption, high density, magnetic storage, electronic device, magnetic resonance imagery, and the magnetic tunable filter. These applications have made spinel ferrite nanoparticle of significant technology. Okay, uh, after that, please, the next. Uh, uh, Hello. Today I will talk about the aim of the work, material,
Yes, sir.
experimental technique, the preparation of the sample, and the characterization. And I will talk about also results and discussion and the conclusion of our work. The aim of our work is to study and is preparing the spinel ferrite with the chemical composition: manganese 0.5, iron 1.5, magnesium 0.5, nickel 0.5, oxygen 0.4. We prepared the spinel ferrite by using auto composition method, and we use the polymer material by casting method. The structure and the morphology and the optical properties was examined in detail. Furthermore, the electrical parameters such as permittivity, AC conductivity, and the electric modulus were investigated. Okay? Yes. Now I will talk about the sample preparation. How we prepared this sample. At the at the first at the first we prepared. Please, the next slide, please. At the first, the spinel ferrite was prepared to base on a flash auto composition technique. We use ferrite nitrate manganese nitrate, magnesium nitrate, and citric acid. And by using the flash auto composition method, and after that, the ash powder have been ground to fine powder and annealed and temperature 700. Believe, yes, this picture show how to prepare. This slide show how we prepared the sample. The spinel ferrite, we prepared it by a flash auto composition method as seen in the first picture. And after that, the polymer film has been prepared by casting method as shown in this figure. After that, the sample characterization, we have make a lot of characterization on the sample, like X-ray diffraction and transmission electron microscope, scanning electron microscope, Fourier transformation, FTI, UV absorption spectroscopy, and dielectrical spectroscopy measured. Let us now see the analysis of this. No, yes, after the, please, result and discussion, please. Yes, X-ray. The first slide, please, in the result and discussion. I will talk now about the X-ray diffraction of the of the nanofiller. It is vinyl ferrite. This figure show the X-ray diffraction pattern rate field refinement. Yes. This one, please. Okay. Now I will talk about the X-ray diffraction of spinel ferrite material of nanofiller which we prepared. This X-ray diffraction pattern rate field refinement of spinel ferrite that provide a confirmation the formation of face center cubic spinel structure of space group FD3M with lattice parameter A equal 8.4. The structure, and after that we will see the structure of BVA films with diffraction with the X-ray. The next slide, please. Yes, this one. This figure show the difference between the amorphous structure of polymer BVA, and after that, when we add the vinyl ferrite, the structure of the BVA was changed, and we the X-ray confirmed that the distribution of the vinyl ferrite into the BVA polymer film. Yes, this is the transmission electron microscopy of our spinel ferrite. From this figure, from this figure, we can confirm that the preparation of spinel ferrite in nanostructure with crystal size about 25 nanometer. And after that, we see the scanning electron microscope. The scanning electron microscope cross-section image of BVA and spinel ferrite BVA nanocomposite film with different doping. The cross-section of pure BVA reveal a line and the parallel texture as you see. Insertion of spinel ferrite in the BVA polymer with different doping concentration can be seen in this figure. As the doping of nano particle increasing from 1 to 5 into the polymer matrix, the small doping reaches 1 nanoparticle enter BVA texture without any change in the alignment of the BVA texture as you see. The excess of the excess of spinel ferrite segregated at the texture as seen from red arrows, increasing the ratio from 2 to 5 cause flow in the texture alignment that increase with increasing the ratio of doping as seen in this figure. After that, as you seen in this figure, we also analyze our sample by using FTI spectroscopy. This figure reveal the FTIR spectrum of no FTIR please reveal the FTIR spectrum of BVA. Yes, thank you. Reveal the FTIR spectrum of BVA and spinel ferrite BVA nanocomposite. The FTIR spectrum show a broad and strong band center at different wave number. The spectrum accepts several vibrational modes at different wavelengths, which is due to the BVA polymer. And you can see there is a different in the structure by adding the spinel nanoferrite. Now I will talk about the optical properties of the BVA after and before adding the spinel ferrite. The next slide, please. Yes, this figure shows the absorption spectrum of BVA and spinel ferrite BVA nanocomposite film with different amount of doping. As you seen from this, as you seen from this figure, as the wavelength increased from 300 to 1400, the value of absorption decreased to lower value, which appear obviously in BVA film. But this reduction in absorption become less as the doping of filler nanoparticle increase. And as the wavelengths increase behind 1500 nanometer, we observed a multiple of absorption peak for spinel ferrite, and this oscillation is due to interaction between the matrix of polymer and the instant light. The value of the observed linear optical absorption were elevated by doping with nanoparticle, and the absorption value increased as nanoparticle increase in the polymer matrix. With a small shift to longer wavelengths, the absorption edge. This shift is translated into a change in the energy band gap and the inner band of optical transmission, as we will show later. After that, the next figure show the recorded transmitted spectrum, where the next slide, please, the transmit shows that yes. This figure show the transmittance spectrum. As you seen from this figure, the transmittance increase as the wavelengths increase, while decreasing as and as you seen the transmittance decreases as the filler nanoparticle increase. These change are due to the interaction of spinel ferrite in BVA. The transparency of the BVA reached, as you seen, to 80% in the visible and UV region, and it decreased to 60 in the far infrared region. In order to determine the energy band gap in indirect and indirect, we calculate the optical energy band. We can use the primary absorption associated with the extension of the electron from the valence band to conduction band. In this, to calculate the optical band gap indirect and indirect, we use tau equation used to calculate optical energy gap. As you seen from this figure, as the nanofiller increased in the PVM material, we found that the optical band gap decreased. The decrement on in the case of direct and indirect energy gap is due to the vibrations that happened at polymer disorder level, which appear as the result of polymer frame alternation caused by nanofiller, and also due to the increase of the localized states in the band gap. This helps to improve the carrier interaction in the valence and conduction band. After that, we prepared this sample in for using these materials in the optical application. So we must to so we uh, so we calculated the excitation coefficient and the refractive index. As you see from this figure, we found that as the nanofiller increase, we found that the excitation coefficient and the refractive index increased with the nanofiller, as you see from these figures as shown. Yes, this rise in the improvement and the increase in the refractive index is due to the filler nanoparticle increase backing density of the film, number of atoms per unit value, which also increase the scattering effect and show down the light speed in nanoparticle films. In addition to, we also measured the dielectrical properties for this material. As seen from this figure, we found that as the frequency increased, the permittivity of the sample decreased. But as we increased the nanofiller material, we found that the permittivity of the sample increased with increasing the nanofiller. It can be shown. Yes, yes. It was noted that as the doping of nanoparticle increased, the value of permittivity increased up to 3% of the filler after they began to decline slight with 5% of fillers. The enhancement of the permittivity of the doping of nanoparticle in PVA matrix increases is due to the interaction of the nanofiller nanoparticle with the PVA change enhance the partial Doppler ordering and lead to formation of charge carrier that increase the polarization, also due to exchange between the iron 2 and the iron 3. In addition to, we measured also the AC conductivity this figure shows the AC conductivity as a function of frequency of BVA and the nanofiller. As we see, we found that sorry. Yes, now I will talk the conclusion. Polymer nanocomposite based on BVA and doped with spinel ferrite are prepared using the casting method, and and after that the spinel ferrite was prepared by using auto composition, or result confirms that all properties of BVA were enhanced after doping with spinel nanoferrite. XRD shows the formation XRD shows the formation of cubic spinel ferrite nanoparticles and the semicrystalline phase of BVA. The transmission electron microscopy confirmed the formation of phase center cubic spinel structure of manganese, iron, magnesium, nickel nanoparticle in nano size ranging from 15 to 25 nanometer. Scanning electron microscope show a good dispersion of the nanoparticle at the interface region of BVA matrix. In addition to the FTIR spectrum demonstrating the strong bonding connecting between the spinel ferrite and the BVA chain. UV visible absorption spectroscopy was used to investigate the optical properties of BVA and nanofiller nanocomposite film. The optical results show that the positive effect of doping nanofiller in BVA matrix. The dielectrical analysis shows that nanofiller with BVA nano have a higher value of dielectrical permittivity and exhibited lower value of dielectrical loss, electrical modulus, and impedance than pure BVA. AC conductivity increase with increasing both nanofiller and frequency. So, finally, we can see that with increasing the doped, as we see from the results, we can use these materials, and we can use this polymer with doping with different material with optical and dielectrical application. Thank you very much.
So thank you
Thank you very much. Thank you.
very much, Dr. Abusa, as you have given a very good explanation about the polymer doped spinal fluid materials. And here we had a wide knowledge sharing about the material characterization and application of that polymer doped spinal fluid materials. Thank you so much, sir.
Thank you very much. Thank you.
Thank you so much, sir. Participants, thank you very much for joining us. We put a feedback link soon in the group, and tomorrow session will be intimated you about the timing.
Hi, sir. Hello. I am hearing you.
Sir, can you able to hear my voice?
Yes, I am hearing you.
Dr. Abusha? Sir, can you be able to hear my voice? Dr. Abusha? Dear participants, we can wind up the session now. The next session of FDP will be communicated to you through the group. Thank you for your support. Thank you, sir.
Thank you very much. Thank you.
Thank you, sir. Thank you so much for joining us, sir.